Okay, welcome to session number 12. I probably will do it in two parts about mathematical methods of signal processing. The two main goals of my course today will be to show you, and really in the meaning of showing you, not to bombard you too much with a lot of convergence issues. So we will see different types of convergence with some comments of what the general background is. The second part will be to guide you a little bit through the universe of function spaces that I think one may use or should use when one is discussing mathematical questions in the context of signal processing or so. So you may recall that we have so far introduced convolution for the bounded measures. We have identified those measures which are introduced by nice density functions, meaning compactly supported continuous functions, and we have taken the limits. Now, the integral, which appears as a Riemann integral for those nice functions, can be extended, and we still use the integral symbol over RD, multiple integral if you want so, for those elements which are actually measures, which are so-called absolutely continuous. But we don't have to care, we just have a linear functional and that can be extended. It happens, and that's why this integral sign is a serious integral, that it can be justified using Lebesgue integration theory, but this is not what we want to use. So clearly, when you take a limit of a functional in the L1 sense, then you can still use the L1 norm, which is, so to say, in the ordinary world, the integral over the absolute value of the function. And so we get a norm. We can measure the size by this L1 norm. Now, in the world of measurable functions, you have to be careful because norm 0 only means that the function is 0 almost everywhere. So correctly speaking, you have to talk about equivalence classes. But equivalence classes are not distinguished once you are using those functions through an integral. So it's really better to think of bounded measures. And if two functions create the same linear functionals, we consider them as equal, and that's quite normal. Now, we have seen, and that was one of the main subjects in last session, that we have the Riemann-Lebesgue lemma. So all these very nice or nicely approximable bounded measures have not only a Fourier transform. So when you look at the eigenvalues for the eigenvectors appearing from the pure frequencies, you're getting some number, which is a function of the frequency on the frequency domain. But you also know that the nice functions have a decay at infinity. So the short formulation is the Fourier transform maps L1 into C0, so into space of vanishing functions. You also remember that the Dirac Delta has a Fourier transform which is constant 1. Dirac Delta is the unit for convolution, constant 1 is the unit for multiplication, so clearly constant 1 does not decay. On the other hand, L1 cannot have a unit because exactly of this property. The unit would have to be constant 1, and so we have a problem with Riemann-Lebesgue. Now, as a replacement, that's a very typical situation in the functional analytic setting. You're saying, well, maybe we have something which approximates the identity operator. And the meaning of this is in the sense of the so-called strong operator topology. So think of the identity system, and that's represented by convolution with the Dirac 0. That's another equivalent formulation of what is known as the sifting property of the Dirac Delta. So it's almost a trivial statement. But you can approximate the Dirac Delta by something which, when you look at the action on individual elements from L1, for example, or from C0, here we're concentrating on L1, you're getting almost the same effect. So a bounded approximate unit is a bounded family. So boundedness is condition number 145, which in its action, you use the convolution operators, is approximating the function f. Now, I'm writing G rho because it can be an abstract parameter, but you should think now, I will use this of this so-called S0 operator. And the S0 operator is the measure preserving or area preserving compression. So think maybe of a Gauss function or a box function and assume that you are compressing it. So each of those functions has integral 1, and that gives in the limit some function, well, not really a function, it gives a measure. And in order to say it has integral 1 just means you integrate it and you apply it to the constant 1. So Dirac at 0, located at 0, evaluated at the function constant 1, which is a bounded continuous function, is of course giving 1. This is what usually is described as mysterious property of the Dirac delta. It's 0 except 1 point, and that is so strong plus infinity that you're getting the integral value 1. Now, I have put also in the script a note and an illustration with GeoGebra of a statement in the book of Canval, because he is saying that this is a misbelief. So people shouldn't think that all the time the Dirac at 0 has to be plus infinity, and he gives an example where it can be minus infinity. Now this is highly problematic because you can give me any value and I find you a sequence which is a Dirac sequence in this sense, in the sense of the approximate unit, and the pointwise values at 0 converge to this value. Or you give me you ask me how to take an erratic oscillatory sequence and I produce something which has this prepe. So it's simple that you cannot say anything about the pointwise values of measures. That's the main point. That's the correct statement. So it's not that something is going to infinity plus or minus. It can be 0. It can be anything. Pointwise values don't make sense. And we will have a statement replacing the fact that Dirac is 0 at all the points except 0. We will say that support of the measure is just 1 point, and that's a different statement, but that needs some time a little bit later. Now, the statement, now this was an abstract definition, but the concrete statement and also the explanation and the proof will give you a nice illustration. It's saying that if you start with a continuous function with compact support, so you apply it to a function, and then you're taking another function which has integral 1, I think this condition was not stated here, then you will have convergence in the subnorm sense. But if you compress a function g, then the support will be smaller and you can control the support of this convolution product. So everything is living in some big interval or in some ball of finite radius. And therefore you can conclude that you get from the convergence in the subnorm sense, from uniform convergent, the L1 convergence. So just think that the first statement gives you that an upper Riemannian sum of this difference is very small in terms of amplitude, but the area is finite, so this is obvious proof. We will discuss these pictures a little bit later, so let me skip them. Now, the formal proof for such a statement is the following. And actually, I'm not sure if I use the correct symbols here, but we have two functions. One, both of them are compactly supported, and we compare them in size. Now, the trick is, if I assume, which I didn't spell out here, it's written clearly, that the integral over g is 1, then you can, of course, write f of x as an integral over y. So remember, stretching is area preserving. So I increase the amplitude once I squeeze the support. And the integral is with respect to the variable y. So f of x is just a constant. But inserting this into the estimate, so instead of the convolution product minus f, I'm writing integral over S0, and there is no argument. And then you can replace and go to the definition, the integral by f of x minus y minus f of x. So this is a difference of two integrals. And of course, this is at most the integral of the absolute value of the difference of the arguments. Now, this looks nasty, but we observe that the variables here are controlled by by the support of the compressed function S0 of g. So assume that the function itself, support of g, is in some ball of radius r, so think of a circle, and then you compress it, you make it smaller and smaller, then this fixed radius is shrinking, and the new radius, everything is concentrated in a ball of radius rho times r. Capital R is fixed, it's given with the support of g, and the rho can be controlled, and you make it smaller and smaller. So of course, now you can replace, to get the same integral, but now you replace the variable to this ball, and that ball is a very small ball. But we know that f is a compactly supported continuous function, which is uniformly continuous. So all the possible differences are controlled by the size, just because the absolute value I should write here is at most rho times r, and so it's small. Now, this already gives you that the differences are uniformly small for all the values x, and we get the supernorm estimate. And because of the reported joint support, also the L1 norm can be estimated. So we get kind of, for the nice subspace of continuous functions, with one having integral 1, that's the compressed one, applied to any other from the dense subspace, we can get this approximate identity. But this is not what the statement says. We claim we can do it for every element in L1. So the F should be general. And actually also what we can see is that the function F can be general. So I will try to give you an indication of how to derive from this kind of the key statement. That's really where the analysis takes place. And the rest is what some people call abstract nonsense. You're just approximating correctly and try to have complete control over the situation. Now, statement here is written correctly. The integral of g should be 1, but the integral is of course the same as integrating against e to the 0. So it's the Fourier transform at 0. Should be 1, and then we compress this family and we say it's a bounded approximate unit. Now the first statement is that if you put absolute values here, maybe you get some larger number, but it's integrable because g is in L1, and compressing it, it does not change the L1 norm, so it's clearly a bounded family. Now, what does it mean to say it's a bounded approximate units? And I do the standard role game. I'm suggesting that, well, please give me some f and ask me with some tiny epsilon to do an approximation. What I have to find is some parameter rho such that you can test my claim against any rho which is at most the one that I'm suggesting. And you will have to find st rho of g convolved with f minus f, and L1 norm is less than epsilon. So I would have not achieved the result if I provide you with some rho and you find at least some parameter rho which is very small, smaller than the given value, but still the difference is bigger. So we'll try to avoid this. Now, because you can rescale this condition, so if f has norm 5, then you can divide everything by 5. So we can assume that f has norm 1. And it's quite obvious that you will say, okay, if the g and the f would have compact support, everything would be great, and we are already done. So we will do an approximation. Now, there is some nasty side condition, which is the integral condition. So we will approximate the function g in L1 by definition by continuous function with compact support. But will that mean that also the new approximating function has also integral 1? There are two ways to deal with this problem. Either you're saying that you can modify any approximation such that also this extra condition is satisfied, or you're arguing, and that's what we do here, that if you approximate to some extent with some value eta, and we will choose eta later on, then of course also the difference between this integral, which I write as k hat at 0 minus 1, but 1 is by assumption the g hat of 0, so it's a difference of two values of the Fourier transform, Is at most the maximum of the difference because we have C0 functions which are continuous. So the sup norm is the max, it takes a maximum. And that maximum is of course known of the difference of those two functions is controlled by the L1 norm. You can think of this in the Lebesgue sense or in the limit sense of bounded measures. So it's this difference which we make small. So it may not, K0, K hat of 0 may not be exactly 1, but it will not be close. I'm preparing this because that will be useful later. So what we really want to do now is we try to see that this modified value will be small. And then we will, what is the statement? Yeah, we can also, sorry, I didn't write here. I approximate the function f in L1, and I'm not sure if I'm using the right lemma here. So I'm approximating now with a compactly supported function. Maybe we can assume for a moment that the f is in compactly supported and continuous. Maybe I'm not citing the right lemma. I made different versions of the proof here. Okay, so now what we have to estimate is that, well, what happens if we look at the difference between the compressed approximating k and the compressed function g, which we should use. And then, of course, you use the distributive law, and you say, well, this is S0 of k minus S0 of g, and then the difference convolved with g. So you can pull out this and write, again, the operator S0 is linear. This is a compressed version of k minus g measured in the L1 norm times the L1 norm of f. So remember, the convolution product can be estimated in the L1 norm by the product of the L1 norms. Just because the L1 norms are just special cases of the bounded measures, and the bounded measures are submultiplicative because it's the composition of operators, which is essentially written here. Now, S0 is isometric, so you can discard the operator S0, and you get k minus g, and we have assumed that f has norm 1, therefore we get k minus g L1 norm, and that was supposed to be less than epsilon. Now, using the triangle inequality, and that's the standard trick to say what you want to have, if we compress the given maybe infinitely supported function, it could be a Gauss function, for example. It decays very well, but it has not compact support. We compress it minus f, and we compare it. Then we say, well, let's go from the function g, which is not yet controllable, to the function k, which has compact support. But then from the compressed version, we go to the scaled version of f. So this is just another version of our lemma. And then we say, well, this factor is not the right one. We would like to have 1 times f. And so we get 3 errors, and one has to be careful in checking the order. So first we will say, we want to make sure that eta plus epsilon over 3 plus eta is less than epsilon, so it's most convenient to assume that eta is epsilon over 3 or anything smaller. So given that value eta, we choose some k, which is making the first and the last term of the previous estimate okay. So we get eta from the first term and the last one. Now, and that's very important to keep the order, once this is fixed, we can do with the k whatever we want. And it's also very important that this first estimate, due to the line above, does not depend on rho. So while we are changing the parameter rho in the middle term, the first and the last term are uniformly under control. They are never getting more than 2 eta together. Okay, now the k, if the k is fixed, we can use the previous lemma, maybe with the version that f is already in L1, to get that we can get also this term less than epsilon or epsilon over 3 to be sure, by making rho smaller than the required parameter rho 0. So if you would come with your G, and I would choose the rho such that the middle term is less than 3 over epsilon, with the help of the deviation through the K, we would be completely under control. Now, I was moving a corollary to this place as a consequence, which actually is a little bit too early, so I will move it a little bit later. But it's an interesting statement. It's the statement that the space of band-limited function, I use this particular symbol, that's an ad hoc symbol. I write L1 sub BDL for band-limited function. So I'm saying that the functions f in L1 such that the support of f hat is compact is a dense subspace. So every function in the Fourier algebra, in the Fourier algebra is can be approximated by a compactly supported function. I have a short question in the chat. I will reply. I will give it later because we don't need it at the moment. Okay, so what I will do to do this is I will use our relationship that the delta, the triangular function, which has been arising as the convolution product of a boxcar function with a boxcar function. And this triangular function centered at 0, so it's starting from -1 to +1 is symmetric, so it's equal to its flipped version. It is the Fourier transform of the sinc square function. Now this is a little bit jumping ahead because what we have done is we have computed the Fourier transform of the boxcar function, and that's the sinc function, the one which decays poorly and oscillates with positive and negative values. But the convolution square is giving you absolute square of this real valued function. So in reality, we have that the Fourier transform of the Dirac triangular function, is the sinc square function. That also the opposite is true, that we can come back, and actually the inverse Fourier transform will be the Fourier transform combined with the flip. That's why I have the flip here, which has no effect on the triangular function. Is a little bit too early, but let's accept it for the moment. So the main point is we have this relationship that you can take any function which has integral 1. So I'm jumping back, and maybe that explains your question. I'm jumping back. So this is the statement of a bounded approximate unit, this last line in 79. It says, we have a family of compressed functions, but what I need is, and that's not spelled out here correctly, what I need is the integral has to be 1, or the same is the Fourier transform of this function has to be 0, at 0 has to be equal 1. And if I use it, I get a bounded family. That's why we talk about a bounded approximate unit. But in its action, it approximates the action of the identity operator. So that's what we want to use. And we have this version also for general functions. So you can choose any function. Here the statement is more correct. Any function g in L1, and you compress it, and it has the same effect. And you see here I was proving this statement, that how it acts. Now assume that I take the sinc square function, and we've seen it's decaying like 1 over x squared, so it's integrable and we can use it. And the integral is the Fourier transform at the origin. The Fourier transform is the triangular function, and the triangular function at the origin is 1. So that's our condition is satisfied. But what is the effect? What can you say about this approximating function? So we are convolving a function with the sinc square function, and which is a non-negative function. So the new arising, we are getting a function which is of the form S0 of G and convolved with F. And I've claimed that this is a thing which has compactly supported Fourier transform. So, okay, what do we have to do? And this is what you will learn over and over again. We have a convolution product. We go to the Fourier transform domain. So convolution goes into pointwise product. So instead of the Fourier transform, we take the Fourier transform of each part separately. So f goes to f hat. Convolution goes to pointwise multiplication. St rho is the compression, goes to dilation, so stretched version. So it's d rho of triangular function. So I will also demonstrate this here, but the d rho of triangular function is very easy. It's just you stretch the triangular function, and instead of starting at -1, you start maybe at -100 and go up to 1 at 0, and you go back in a symmetric way. So these functions are all of them compactly supported. So everything is vanishing where the triangular function is vanishing, and rho is getting small. So 1 over rho is getting bigger and bigger. So it's a dilated version of the unit interval or unit ball in multidimensional situation. So it's a ball of radius 1 over rho, and that's enough because we know that these guys are approximating our f in the L1 sense. And the new function, this approximate, is having a compactly supported Fourier transform. So we're essentially saying we go to the Fourier domain, we manipulate the Fourier transform. Later on, you would say we are filtering f hat with a triangular profile, and that is what people also have called in the classical setting the Feyer summability method. And that tells you you can approximate a function by taking parts of the Fourier transform. I must say I prefer actually a trapezoidal function because that leaves at least the inner frequencies untouched and makes some decay on the outside. But the naive way of doing it, meaning you cut off the Fourier transform domain, is not a good idea. And this is just something I would like to show you first, and then we will discuss it later on. You can take the rectangular function, and we have seen this as a Fourier transform, which is the sinc function. It doesn't matter. So yes, it's true, it decays at 0. It decays to 0 at infinity. But what we do now is we could truncate that sinc Fourier transform instead of take the inverse Fourier transform. And then we would get something like this. So this is a good approximation in the L2 sense, as we will see. It's the best approximation, but it has nasty effects. So it's overshooting, undershooting, and so this is not good. And if you look at the Fourier transform domain, you will, sorry, I will try to make it. You see that you have this behavior of the sinc function, and at some point you're just sharply truncating it. So you can also look what happens if you change the place where you truncate it. What is, however, much better is to say I'm taking something like a smooth plateau function on the Fourier transform domain. So that means I'm convolving with something which is very much like this. So then a smooth version or an approximation of a rectangular function by a smooth function will look like this. And most people would probably like this better because the rectangular function takes values between 0 and 1. And the new version is like moving material from the corner here and moves it down just to smooth it out. But it's not overshooting and not undershooting. So you look here, this is what is called the Gibbs phenomenon. And that's not so nice because you're having overshoot, undershooting. And that's considered as one of the bad effects of partial sums of Fourier series. So we are talking about Fourier transforms, but this situation is very simple. Now, just a short word about the situation that Canval is describing or so. Look at the red function here. This is a sum of a Gauss function. The green template is a Gauss function, which has integral 1, so it's a probability measure, and I take a shifted version, shift by -2 and a shift by +2, and I take a negative. So I have a total integral of +1, -1, +1, which is of course 1. Now, if you compress it, let's say you compress by a factor of 10, then this value will be -10, and these values will be +10. So if you look from the big distance, you see one total mass, and everything is concentrated. If you look only at the value at 0, it will go to minus infinity. But the same picture without this middle term, you could take one Gauss functions to the left, another to the right, maybe make sure that the midterm is small or goes to 0. Yeah, maybe just move them also a little bit to further apart or so. And then you compress this maybe mass 1/2 to the left, mass 1/2 to the right. And then you would say, okay, this is a sequence which is a Dirac sequence, so it works as a convolution operator, almost like the Dirac Delta, but the limit of the values at 0 are going to 0. So it just means don't talk about function values of measures. Now, for this session, I have prepared various things, and finally I realized that many of the arguments that I'm using in the estimates are quite similar in terms of what the structure of the proof is or so. So I decided, and I hope it's helpful, at least if you're looking at this more carefully later on, to distill out of these different proofs the abstract structure. And abstract, of course, means it's not that it's not meaningful, but that you can apply this situation in many different situations. I'm actually exploring further applications of these principles because I have the feeling that this is a kind of argument I have been using over decades, and I'm kind of getting used to it, but now I have started to even formulate it more abstractly. So this is something that you will not find in any book, but it's kind of harmless functional analysis. So just think of what we had before. We had this approximate identity, and we were saying, well, we are manipulating the G and the F. We had before the convolution of bounded measures with C0 functions, and essentially part of the proof was to say, well, we can approximate a bounded measure by compactly supported measure. We can approximate a C0 function by compactly supported continuous function. And so the repeated argument of we approximate and we get something by doing some serious analytic work, as we have done now with these two functions with compact support. And then we do abstract nonsense. So I'm showing you what is the principle of abstract nonsense in this context. I have two such statements, and I would like to explain them quietly before taking the break. So the first thing is we have very often the situation that we have a bilinear mapping from a pair of Banach spaces into a third Banach space. So just think of, may have the Banach space B1 could be the continuous functions vanishing at infinity. The B2 could be the dual space, and if you put them together by taking mu of f, we get a complex number. So B can be a degenerate space. It can be just a complex numbers with absolute value. Or we have convolution. We have L1 convolved with L1 is in L1, and all three spaces would be the same. And we would show that convolution is kind of easy to do when all of the ingredients are continuous functions with compact support. And we would like to extend this continuity of convolution to all of L1, as we have done more or less already, and so on. So such situations are quite clear. So bilinear means, to give a formal explanation, you have something where you have a first and a second coordinate. If you fix the first coordinate, you have a superposition and scaling invariance in the second argument. So m of b1, and then you take, I don't know, 3b2 plus 5b2 prime. You can recompute it in the usual way as if it was an ordinary multiplication. So m is indicating we have a kind of abstract multiplication with all the rules. And bilinear, of course, means it's also in the first variable linear. So if you fix the second coordinate, it's linear with respect to the first linear coordinate. Yeah, another bilinear object that you know is the scalar product of two vectors. You are in Rn, you take the scalar product. You have these standard rules. Now, we are in function space or in functional analysis, so we have to look at boundedness. Boundedness means there's a constant that allows you to control the size of this multiplicative effect by the product of the norms of the input spaces or so. And then you also have that you get a function which is continuous, and you could improve the converse, but that's the main point. You have a sequence Fn going in the sense of the norm of B1 to F0. I like always to give the label 0 to the limit elements. And you have another sequence Gn in the second space, and the limit in the B2 sense is the G0. And then the claim is that, of course, what you expect is that M of F0 G0 is just the limit. We are all the M is going into the Banach space B by taking the limit of Fn Gn. I mean, if you go to the proof, you could even say that M of Fn and Gk, so you could have two different indices. If both of them are large enough, your mixed abstract multiplication product will be close to M of F0 G0. But I think it's enough to do it for the diagonal case. So again, statement of the goal. You're challenging me and you're giving me some epsilon, and I have to find some index n0 such that whenever you check with an F and a Gn which has an index which is behind the index that I have proposed, you should be able to, or you should not have a chance to contradict my claim. Now, very similar to what we had before, there's a first step which is kind of convenience in order to avoid a side step later on. I'm saying, well, if you have a convergent sequence, it will be bounded. Well, why? Because all the elements Gn, if they are getting closer and closer to the G0, their size will be controlled by the triangular inequality. So you write Gn equals Gn minus G0 plus G0. But you put brackets such that you have the difference between Gn and the limit and the limit element. But if we make the index large enough because of convergence, that difference will be small. So let's say we make it less than 1 away from G0. So that's one constant that we fix because we will need it later on. Now we are doing the same proof that you would do to prove continuity of multiplication. M of Fn minus F0 Gn is estimated by introducing an intermediate term. You're free to choose Fn G0 or I put F0 Gn. So you add it, you subtract it first, you add it, and then you put the triangular inequality. So the main point is just how can we control it? Well, this can be controlled because now the Gn is fixed. We pull out the Gn. The multiplicative estimate is with a constant, and then we take the difference of Fn minus F0 in the first norm. But the Gn is at most C1, so we move that constant over to the C, and the rest is Fn minus F0. Well, the second term is done in the same way. It's now easier because F0 is already a fixed element, which we know. So what we will do is, of course, to make those terms Fn minus F0 and Gn minus G0 in the first or second space as small as we need it, so that if we multiply it with this constant which appear in the estimate, we will get epsilon over 2, and we have two terms. Each of them gives epsilon over 2. And of course, I can achieve both of these estimates by choosing n large enough. And to be sure that also the first part can be used, we are choosing the n0 behind the C index n1. So we have a very easy proof, which is just like continuity of multiplication that gives us this. The next thing is a little bit tricky, and I will maybe first read it and then we take a break so that you have a chance to maybe ask questions. See, the reference has to be corrected. So if you see this, it really looks like abstract or abstract nonsense, but I was distilling it from several proofs, which I thought, oh, they all have the same structure. So I'm using the bilinearity, so I'm assuming we have some M, and for the application I have to always to explain what the M is. And we have a B1 and B2 space. And we will prove something for the dense subspace. And in the general situation, you have one for the first space and another C2 for the second space. And we have some operators. So it might be the discretization operators, the compression operators, all these operators. And that's why it's very useful to really give them names instead of just writing the compressed version with arguments or so. And so the point is these operators should be uniformly bounded. So there's an alpha missing, so it should be written T alpha in the operator norm of B1 should be controlled by some constant. I was running out of constant, so I just put the ordinary B here. It's just like a C, another constant or so. But what does it mean, the operator norm? Well, the magnification, if you apply the T alpha here, it's correct, should be uniform with respect to alpha in the B norm. So T alpha F is in the space B, and you can control the size by the norm of B up to a factor B. Most of the time, B will be actually 1. Also, there will be a kind of limit operator, which is, you can say, the infinite compression in our application here. So, and that operator, also the T0 should have the same property. So T alpha and T0 are badly formulated here. Now, what I want to do is to say, well, if we're able to control this behavior of the operators within a bilinear situation for the elements of a dense subspace, and I tried to use different letters, K and F, that's for the elements in the dense subspace. If you give me any pair, you apply the operators, you would like to see what happens, and you get a limiting operator, and that can be paired with the F. And then you would like to extend it and say, oh, no, I can extend it. This M is continuous, and we approximate the G, the general element G in B1 by K from the dense subspace. You're giving me some H in, let's say, in C0, you approximate it by F in compactly supported with compact support. And you would like to have the same relationship in for the full space or so. So I think it's a good moment also in terms of timing to stop here. I am completely understanding that the moment you're just astonished by these kind of expressions and how can such abstract things be useful, but I will first give you the proof and then various applications. I don't want to go through all the applications now, but I think this lemma is something we will come back to a situation that we will come back frequently or so. So let's take a break now, and I will stop the recording and resume with another recording in a moment.